This animation describes the process of determining strain pole figures from diffraction experiments. Most metallic samples appear homogeneous on the level of 100 millimeters. As we zoom in further, we begin to see inhomogeneity. At the scale of 100 micrometers, individual grains are clearly visible. In this image, taken from a sample of stainless steel, the grains are darker regions bounded by bright lines. Each grain is a region where the crystal lattice is continuous. Different grains may have different morphology, as well as lattice orientations. Here, a possible orientation of the underlying FCC lattice of this grain is shown schematically. Other nearby grains may have different lattice orientations. These attributes may be distributed in a statistically non-uniform manner in a sample as a result of thermomechanical processing. Furthermore, the distributions of grain morphologies and orientations may exhibit spatial correlations. Let's examine 4 different grains. The sample axes give us a point of reference to compare the orientation of each grain, represented here by a single unit cell from the respective crystal lattices. A set of crystal axes may be fixed to the crystal lattice to define its orientation. For cubic crystals, a convenient choice for the directions of the crystal axes are the edges of the unit cell. If we illuminate these crystals with X-rays, a portion of the radiation is transmitted and the rest is scattered. The portion that is scattered, or diffracted, can be thought of as reflecting off planes of atoms in the lattice as if they were mirrors. These sets of crystallographic planes may be denoted by 3 Miller indices, H, K, and L, and have a characteristic spacing. Notice that the scattering vector is the normal to the highlighted planes and that it bisects the incident and diffracted beams. Not all sets of planes, however, reflect X-rays simultaneously. If the sample containing the crystals is rotated with respect to the beam, diffraction from a different set of crystallographic planes may occur. Here, diffraction from a different set of crystallographic planes is shown. Despite the analogy between crystallographic planes and mirrors, unlike specular reflection, diffraction does not occur for arbitrary angles of incidence, denoted by theta. Rather, a specific condition known as Bragg's law must be satisfied. Bragg's law is based on the principle of interference. Take a set of planes with spacing d. If we use X-rays with wavelength lambda at an incident angle of theta as shown, why do we observe diffraction? Notice what happens as successive wavefronts denoted by the yellow, red, and green lines pass over the atom sites. Each atom radiates isotropically, giving off spherical wavefronts with wavelength lambda like ripples in a pool. Notice, however, that these scattered waves only overlap in 2 very special directions, along the transmitted and reflected beams. If we were to change d, lambda, or theta independently, the scattered waves would be out of phase and diffraction would not occur. Here is the relation shown explicitly. If we design an experiment where we fix lambda and are able to rock the sample over some finite angular range, we are sensitive to normal strains along the scattering vector due to elastic strains in the lattice. The fundamental components of a diffraction experiment with in situ loading are the source, the load frame with sample, a beam stop to absorb the transmitted beam, and a detector for measuring intensities of the diffracted beams. Both the load frame and the detector are mounted on high-precision positioning devices, or goniometers. The intersection of the beam and sample defines the center of rotations for each. A point-like detector is shown in the current configuration. It measures intensities over a small angular range. As such, a point detector collects data along a single scattering vector. When a monochromatic beam hits the sample, it is diffracted among discrete directions governed by Bragg's law. When the number of crystals illuminated in a texture-free polycrystalline sample is large, the diffracted beams are distributed axisymmetrically about the incident beam. This scenario is referred to as powder diffraction, and the resulting cones of radiation are referred to as Debye-Schurrer cones. Preferred orientation among the grains in the diffraction volume is manifest as a non-uniform distribution of intensity along the azimuth of the Debye-Schurrer cones. Simply put, where there are more crystals diffracting simultaneously, the signal is more intense. Here the scattering vector Q for a particular Bragg reflection is shown. Recall that Q is both the bisector of the incident and diffracted beams, as well as the normal to the associated crystallographic planes. In this case, it is aligned with the loading direction of the sample. In the case of powder diffraction, a cone of scattering vectors is associated with each Debye-Schurrer cone. If we were to collect data for this specific Bragg reflection, we would be measuring an ensemble average of the subset of crystals that satisfy the Bragg condition in this particular sample orientation. To perform a measurement, the detector is swept through 2 theta until it measures a diffracted beam. Recall that the Bragg angle, theta, is determined by the associated plane spacing and the beam wavelength. To collect data for a different set of crystallographic planes aligned with the same sample direction, both the load frame and the detector must be rotated. Specifically, the load frame must be rotated by half the angle that the detector is rotated. Note that a different subset of crystals is now being interrogated. As the sample is loaded, the macroscopic strain is partitioned among the grains in a complex, non-uniform manner. The resulting changes of interplanar spacings in the crystals are manifest as slight shifts in the corresponding Bragg angles. Here, diffraction for a single family of crystallographic planes is shown for a single scattering vector aligned with the loading direction. Consider the space of all possible scattering vectors. It defines a sphere in the sample coordinate system centered on the diffraction volume. Data associated with each scattering vector, such as orientation, density, or lattice strain, can be plotted as scalar fields on this sphere. Such a plot is referred to as a pole figure. Since normal diffraction cannot distinguish between positive and negative plane normals, data can only be associated with an unsigned plane normal or pole. Therefore, all pole figures are centrosymmetric, and we can restrict our attention to just one hemisphere. A two-dimensional projection, equal area in this case, of the hemisphere with the loading direction at its center is shown at the lower left. A red dot indicates that a measurement has been made and recorded at the corresponding location on the pole figure. To fill in the pole figure for this set of crystallographic planes, we must collect data for different scattering vectors. This is done by rotating the load frame and sample while keeping the detector fixed. Note that each time we examine a new scattering vector, we are measuring the average signals from the subset of crystals that satisfy the Bragg condition in the new sample orientation. For the pole figure to be statistically relevant, these subsets must be sufficiently large, particularly if we are after lattice strains. Measuring pole figures with point detectors is rather costly in terms of time spent. One advantage of employing X-rays as the source is the availability of large two-dimensional detectors such as image plates or CCD arrays. With such a detector, complete Debye-Schurrer cones can be collected simultaneously, expediting the measurement of pole figures. In this schematic, the hemisphere of interest has the beam direction at its center. In terms of pole figure coverage, we shall be able to measure a continuous strip of scattering vectors simultaneously. With the beam normal to the specimen surface, the specimen loading in transverse directions are at points at the top and side of the pole figure. The intersection of the cone of scattering vectors with the highlighted Debye-Schurrer cone is a circle on the pole figure. As before, additional data can be added to the pole figure by rotation of the loading frame and sample. After an exposure with a beam normal to the specimen surface, the load is held constant and the loading frame is rotated about the loading axis. Additional exposures are taken at prescribed orientations. In this manner, data are added to the pole figure ring by ring. Rotation about the specimen transverse direction with associated diffraction exposures produce rings of data oriented orthogonally to the previous example. The area detector reduces the number of sample orientations needed to fill the pole figure. Here is lattice strain data measured from the tensile loading direction of an iron-copper alloy, measured along the sample y-axis at Cornell's high-energy synchrotron source. Data from the 200 family of planes in the copper phase are shown. The coverage pattern of the lattice strain pole figure was obtained using 5 positions of the load frame as shown previously. As the applied stress is increased, the lattice strains in crystals having their 200 directions closely aligned with the loading or y-axis grow increasingly positive. Those crystals having their 200 directions closely aligned with the transverse or z direction grow increasingly negative. These Poisson-like trends are what we might expect considering the uniaxial stress state on the diffraction volume. By combining measurements along many different scattering vectors among multiple pole figures, we obtain a detailed picture of how the macroscopic strain is partitioned among the grains during deformation. Overall, diffraction experiments performed under in situ loading provide researchers with a highly effective tool for assessing the micromechanical state of a polycrystalline sample, as well as its evolution with deformation. As the technology for sources and detectors advances, the methods presented here may be adapted to provide an ever-improving understanding of material behavior.